This video explores how artificial intelligence and data centers are degrading the quality of electricity. Listen to your house for a second. Not the silence, but the hum of the fridge, air conditioning, laptop charger. Now here's a strange idea. Electricity can be good or bad, and near many AI data centers, it's getting worse. I'm not talking about blackouts, but something more treacherous, dirty current, making your devices vibrate more, heat up faster, and age prematurely without warning. The scary question is simple. Could AI be damaging your electricity even if you don't use artificial intelligence? Stay tuned because I'll give you a clear 5-layer plan to prevent a more fragile grid and higher bills for everyone. Good electricity versus bad electricity, the concept that changes everything. When you think about electricity, you think of two states. It's either on or off. You plug something in, it works or it doesn't. But the power grid is actually more like music. It's not just about having sound, but whether it's in tune or if there's noise. In many countries, ideal alternating current looks like a perfect wave, smooth, repetitive, stable. When this wave gets distorted, we get something that sounds technical but is easy to imagine, harmonic distortion. Think of a swing. Push with perfect rhythm, the swing moves smoothly. Push erratically and the swing vibrates oddly. It doesn't just go back and forth, it shakes, does strange things, suffers. That's what happens to electricity when it gets dirty. And this dirt is measured. A typical indicator is THD, total harmonic distortion. Now the important thing is that the power grid is never perfect. There's always some noise, but there are quality limits considered acceptable to prevent devices from suffering too much. One of these limits, used as a reference in low voltage networks, is around 8%. Not because everything explodes beyond that, but because that's where the danger zone begins. More heat, more vibration, more internal stress. And here's the personal impact. If the current isn't smooth, an electric motor like a refrigerator compressor doesn't rotate with clean torque. It moves with tiny jerks. This creates oscillations that translate into two things you can understand. More noise. Your fridge sounds louder and wears out faster because vibration essentially causes fatigue. And this isn't just about refrigerators. It affects fans, pumps, washing machines, air conditioners, transformers, power supplies. Everything with power electronics or motors feels the impact of wave quality. In other words, even if your bill says kW hour, there's another parallel story happening, the story of how that energy actually reaches you. And this is where artificial intelligence comes in, because there's a type of electricity consumer that's growing like crazy and doesn't behave like the rest. The key point is this. It's not just that they consume a lot, it's that they consume in a way that can distort the power wave for everyone else. So why does artificial intelligence dirty the power grid? The invisible semi-trailer plugged into your socket. Imagine two vehicles, a super efficient electric car designed for a precise journey that would represent stable, predictable, typical consumption. Now imagine a giant truck, a semi-trailer that suddenly accelerates, brakes, accelerates, brakes. That's the kind of behavior that's concerning. Traditional data centers already consumed a lot, but AI data centers have a different heart. Accelerators, especially GPUs. And here's the trick that changes everything. A modern GPU, when really working, sucks power like a beast. It's not a smooth consumption, it's a consumption that can be very intense and especially very synchronized. In a normal data center, there are ways to distribute loads, move jobs, balance, smooth out peaks. In artificial intelligence, especially in training, sometimes the goal is the opposite. Everything maxed out. Thousands of chips working simultaneously, coordinated, pushing to the limit. And if you're wondering, okay, but why does that dirty the power wave? Because much of that power goes through electronics that, greatly simplified, doesn't draw current as a steady sip, but in rapid pulses, in chunks. That introduces harmonics, noise, distortion. And why is it more noticeable now? Well, because of density. Because to gain speed, companies are putting more GPUs per rack closer together to reduce latency and expensive cables. That shoots up the power per square meter. Now let's put this in perspective with simple numbers. If you have 100,000 high-performance chips, even if each one uses as little as a small appliance at full power, the total consumption is staggering. Then add what nobody sees: cooling, power conversion, UPS systems, and energy losses. The famous PUE metric exists for a reason. For every useful computing watt, there are extra watts needed for infrastructure, and this scales up to the national level. Organizations like the International Energy Agency estimate that data centers consumed about 415 terawatts globally in 2024, and project nearly 945 terawatts by 2030 in a baseline scenario. That's doubling in just a few years. In the United States, furthermore, the problem is concentrated. When you concentrate electrical demand in one place, the problem stops being global and becomes local. Transformers, lines, substations, permits, and power quality, Here comes another key distinction that explains why AI is different. We have inference versus training. Inference is what happens when you ask a model something. It's usually more stable, but depends on traffic. If millions of people ask at once, it lags. And then we have training, which is the beast, and it's like raising a dinosaur for weeks. Everything maxed out, coordinated, with long, brutal power spikes. And here's the phase that explains why grid operators are scared. The electrical grid has little margin for error. Supply and demand must dance together constantly. If demand rises too quickly, problems. If demand falls too quickly, problems too. And if it crashes suddenly because thousands of installations protect themselves at once, that can be a serious problem. And this isn't hypothetical. There was a day when a network flicker caused many data centers to do just that, disconnect almost simultaneously. So let's talk about the real scare, Data Center Alley and the domino effect. I'll take you to a place that seems made up, but it's real. The Northern Virginia Data Center Corridor, one of the largest concentrations on the planet, where a tiny glitch isn't just oops, power's out. Here it's a domino of automated systems designed for one thing only, never stopping. Because a data center lives with an obsession for continuity and can't accept even a 1-second restart. So they install a survival sequence. They detect anomalies, switch to UPS batteries in milliseconds, and fire up generators to last longer. That's great for them, but can be dangerous for everyone else if too many do it at once. Now, the day of the scare, the initial spark, was something that sounds boring. A failure in transmission infrastructure after a disturbance. A very brief event and a set of micro-voltage drops. A voltage drop for an instant, tens of milliseconds, you wouldn't notice, but sensitive equipment enters panic mode. And what happened next was like a movie scene. Numerous data centers reacted simultaneously. They protected themselves, and in doing so, their demand vanished instantly. We're talking magnitude beyond a factory, like suddenly losing consumption across an entire region. And what happens when the grid suddenly has excess generation? The frequency rises because supply and demand stopped dancing in sync. The deviation was small in number, but huge as a warning, showing that in the future, with more data centers, this could grow larger and network protections could begin to trigger in cascade. And here comes the hardest point to accept. The power grid is a choreography of physics, not business. Operators can react by shutting down plants, activating resources, sending signals, but some things take minutes while the grid can change in seconds. That's why when consumption suddenly drops, the system enters territory ruled by inertia, frequency, and automatic protections. Why does this matter? Because this is how major blackouts begin. Sometimes a blackout doesn't start with a boom, but with a tiny click and a chain reaction. In fact, Europe got a global reminder in 2025 with the massive blackout that affected Spain and Portugal. Technical details and exact causes are still being debated, but the pattern of problem, response imbalance, escalation is exactly the type of scenario operators don't want to see again. So, Virginia's scare isn't a drama, it's a warning because artificial intelligence's future has two equally uncomfortable paths. Either it concentrates even more in clusters, strained local networks, or it moves to new places where the infrastructure might be weaker and events have greater proportional impact, and this is where the human element comes in. When artificial intelligence arrives somewhere, it doesn't come alone. It comes with cement, water, power lines, generators, and neighbors who ask, wait a minute, what's in it for me? This creates a battle for location, cheap land, cheap energy, and the huge catch. Data centers require three things simultaneously: land, power, and cooling. And when a location becomes ideal for these needs, it fills up quickly. And when it fills up, friction begins. In Northern Virginia, for example, success becomes a bottleneck. Connection queues, streaming limits, overloaded transformers, and shifting social attitudes. The yes to everything turns into waiting, but who benefits from this? This is happening in more places because data centers are odd propositions for local politicians. They occupy large spaces, consume enormous resources, may generate taxes, but rarely create as many jobs as expected. So the conflict emerges. Why accept an industrial monster if most value goes elsewhere? And now when one location becomes difficult, companies do the logical thing, find another. That's when places like Arizona appear with vast land, fiber corridors, high voltage lines, and forward planning utilities. Here's what matters. Planning for AI isn't just building more plants, it's building systems that react quickly. That's why you see massive battery projects near tech corridors. Batteries can respond almost instantly, charging, discharging, stabilizing. And that's one of the greatest ironies of this story. What AI needs to avoid breaking the grid looks a lot like what's needed to truly integrate renewable energy. More transmission to move energy from surplus to deficit areas, more storage to smooth peaks and valleys, more control for a flexible grid. But now add the social factor. The Memphis case, for example. When an AI project arrives, it often relies on quick fixes like temporary generators or electricity deals that locals view as unfair. And if this happens in a community with a history of environmental injustice, conflict erupts. And it's not just environmentalism, it's trust. It's about who bears the noise, traffic, local emissions, and who keeps the wealth. So the real problem isn't just technical, it's also political and moral. Who pays for the grid upgrade? The company, taxpayers, users, or neighbors? And if the answer is we'll see, then the easy path is the worst choice. Patches, delays, and an increasingly stressed grid. So yes, artificial intelligence will continue to grow. All these data centers aren't going away. So the question changes, how do we do this without destroying power quality and stability? Here comes the payoff of this video. We have a 5-layer plan to prevent AI from breaking the grid. This is the plan. It's not magic, it's not just a tweet. These 5 layers together make the system resilient, and the good part is you can understand it without being an engineer. Layer 1 is measuring what matters. If you don't measure wave quality, harmonics, voltage events, load ramps, you're blind. And if you don't publish it, you're at the mercy of everything's fine. The first reasonable requirement is simple: power quality transparency in areas with high concentrations of data centers. Not just about blackouts, but what about power quality, events, THD levels, and frequency variations? Because what isn't monitored can't be fixed. Then we could filter and clean at the source, not in your home. If a data center introduces harmonics, the elegant solution isn't buying power strips. The solution is for large emitters to have harmonic filters, proper electronics, interconnection standards, and low noise designs. In the electronics world, this isn't new. Large industries have had to meet regulatory limits for decades. The twist now is that the 21st century industrial giant might be a chimneyless building full of GPUs. The third approach is making data centers flexible loads, which is the most underrated idea. That's key. Some computing, especially training and internal tasks, doesn't need to happen during peak demand. If the grid is at capacity at 7 p.m. during a heat wave, it makes no sense to push AI training just because you can. This is where flexible demand agreements come in, like pausing or reducing load during peak times, shifting tasks to off-peak hours, and distributing workloads geographically when possible. This is literally teaching AI to live with the grid instead of forcing the grid to break because of artificial intelligence. We have the fourth layer, which is rapid storage, batteries that act as shock absorbers. The traditional grid responds in minutes with peaker plants, but some problems emerge in seconds. Large batteries can absorb excess energy, provide instant power, smooth ramps, and stabilize frequency and voltage. And yes, this also helps renewables by converting variable energy into more usable energy. And finally, we have the option of firm power and transmission, the foundation of the system. If everything is flexible and variable without a solid foundation, the grid becomes unstable. That's why companies sign long-term nuclear agreements, develop geothermal, expand gas capacity, and build new transmission lines and substations. Not because they love a particular technology, but because they need something very basic and old-fashioned, reliable 24/7 electricity. The final step is accepting that we need new capacity and long-term planning. Here's the optimistic twist to this story. If done right, AI pressure could become the economic incentive that accelerates grid modernization, battery development, and transmission upgrades, all necessary for electrification and renewables. If done poorly, AI becomes a giant customer that forces quick fixes while others bear the hidden costs. So let's return to the big question. Can AI be ruining your electricity even if you don't use AI? Well, the honest answer is yes, it can, especially locally near data center clusters because they change consumption patterns, introduce distortions and events, and can trigger automatic reactions that stress the grid. And the most unfair part is this can happen without you noticing blackouts. You notice it as noisier appliances, weird failures, shorter lifespans, and a grid that becomes more expensive to maintain. Now, the important part is not inevitable that it ends badly, but it won't fix with just add more panels and done. It's fixed with those 5 layers: measurement, filtering, flexibility, batteries, and firm power plus transmission. And what can you do without being an expert? Well, ask and push for transparency. If data centers are announced in your area, demand they publish power quality metrics and mitigation plans, not just jobs and investment. Don't buy the "it's just a building" story. Treat a data center as what it is: heavy electrical industry that must meet standards and pay for mitigations. Support boring sounding improvements like batteries, substations, transmission modernization. They're not sexy, but they prevent disaster. If you're a business, implement flexible computing policies and smart schedules for non-critical loads. And if you're a consumer, protect the basics. Good surge protection, avoid deteriorated wiring, but don't panic. Real change is systemic. I hope you enjoyed this video about how AI will impact electrical grids in the coming years. In the description, you'll find my AI course focused on learning how to use it for your future work, and I'll see you in future videos. Thank you for watching.